Today we're going to talk more about equivalent resistance and how we can use this concept to analyze increasingly more complicated circuits. For example, consider the series circuit shown on the left. First of all, note that I've labeled the battery with this kind of script E. This E stands for a term electromotive force, or EMF, and it basically means the voltage provided by a battery. It's another term that you might encounter, and I think it's worth at least being aware that this is an expression. It's actually kind of useful because it allows us to express the voltage across a battery in a notation that can't really be confused with the voltage across a resistor. So what does the circuit actually do? Well, we have a battery hooked up to these resistors. The battery is a source of electrical energy. And what happens is this battery pushes current through the resistors. And as current passes through the resistors, some of that energy is converted into heat. You might think, well, this is a stupid circuit. Why would anyone build this? But this is essentially what a toaster is, for example, or any kind of electric heater. It's actually making use of this process. It's taking electrical energy and it's converting it into thermal energy using resistors of some kind. Now that we know what the circuit does, we can ask more detailed questions. For example, how much current is passing through the circuit? There are a number of reasons why I might care about this. For example, a typical battery is only capable of outputting up to a certain amount of current before it stops working properly. And so if I want to power something with batteries, I want to make sure that, it's actually going to function. Alternatively, in a typical building, unless it's like a major commercial or industrial facility, fuses limit the amount of current that can pass through any given circuit, usually to anywhere between 10 to 30 amps. It does this to prevent too much current from flowing through the wires in your home, which could cause heating and eventually can cause fires to start. So if you are watching TV and someone's vacuuming and someone else is microwaving something, if all of those things are plugged into the same circuit, it might draw so much current that everything shuts off. What happens there is the fuse has cut off power to the circuit in order to prevent so much current flowing that it could end up being a fire risk. So I might want to know how much current would all these things together draw. So I know, for example, what do I want to put on different fuses? Another question I might want to ask is how much power is this circuit using? What is the rate at which it consumes energy? For example, I might want to know how long my battery will be able to power the circuit. And to do that, I need to know how much power it's going to draw. Alternatively, again, this circuit is a circuit that heats things. So if this represents a toaster oven, for example, if I can figure out the total power dissipated by each of these resistors, or by the resistors in total, then I can determine how long it will take to toast my bagel. Note that both of these questions are asking about an overall property of the circuit. What is the total current in the circuit? In other words, the total amount of current output by the battery. What is the total power dissipated by the circuit as a whole? I'm not interested in the current through each resistor or the power dissipated by each resistor. I want to know what is in total. And this is where the concept of equivalent resistance really shines. Because what it allows me to do is it allows me to take this circuit with 3 resistors, and it lets me replace it with a simpler circuit that has just a single resistor. I want to make sure that the answer to these 2 questions is the same for both of these circuits, and in this context, we call the resistance of this one resistor the equivalent resistance of the circuit above. We've talked about series circuits already, so we know that if I add a whole bunch of resistors in series, their equivalent resistance is merely their sum. At this point, I can answer the second question we asked, because there's a battery with a voltage E and a total resistance of our circuit, Req, and so V equals IR, and so the current is equal to the battery's voltage divided by the resistance of the circuit. Answering our third question is just as easy. In fact, I could have answered the third question first. We know that power can be expressed as voltage squared divided by the resistance. And so now that I've replaced all the resistors by a single resistor, I know the voltage across that single equivalent resistor is just the voltage of the battery, and so the power is E squared over R equivalent. So if what you care about are the overall properties of the circuit, how much current does the circuit draw, how much power does the circuit use, then equivalent resistance lets you very quickly get at those answers without having to worry about what's going on at each individual resistor. R1, R2, and R3 in this case will have the same current as each other, sure, but they will have different voltages across them, for example, as long as they're not equal. But I didn't need to find those voltages in order to answer all the questions that I wanted to. Other times, you might actually care about what's going on at each individual resistor. Maybe I want to know how much voltage will there be across resistor R2. If I want to do that, the concept of equivalent resistance still is helpful to do it. One way we could do this is we could set up our loop rule, and because we know they're in series, we know they have to share the same current, and then we can use Ohm's law, and we can use that to solve for the things that we're missing. We will get the same answers. For example, we just once again calculated the total current through the circuit starting from the loop rule, but it can be a little bit messier, especially when we start dealing with circuits that are a little bit more complicated. And so a tool that I strongly recommend using is called a VIR chart, or sometimes a VIRP chart if you include power. Here's what you do. On the left, you write down the name of each resistor as well as your equivalent circuit, basically when you've boiled everything down to just this. Then you plug in what you know to begin with. In this case, we're given the total EMF of the battery, or the total voltage of the battery, and we're given the values of the resistances, R1, R2, and R3. At this point, finding out anything else about the circuit is kind of like a puzzle. So notice VIR, right? V is equal to I times R. The voltage across a resistor is equal to the current through it times the resistance of it. So if I have any two of these three columns, then I can always find the third piece of it. So I don't know the voltage across either resistor, and I don't know the current, assuming I haven't done all this work yet, through either resistor. So I can't immediately fill this in. However, I can quickly calculate the equivalent resistance of our circuit. Now I have two of the three variables in Ohm's law in my bottom row, so I can quickly fill in the third. Now I can use the fact that all of these resistors are connected in series with each other and with the battery. So I know that they're all going to have the same current as each other. So I can extend the middle row up. All of these have the same value of I. And now I have two out of the three variables for each of the resistors, and so I can plug in the missing values of the voltage for each. At this point, I can find the power dissipated by each resistor individually or by the entire circuit through any of my three equations, V squared over R, I squared R, and IV. This chart also makes it easy for us to check our work and for it to make sense. For example, I know that the voltage of R1 plus the voltage of across R2 plus the voltage across R3 should add up to the voltage provided by the battery, and I can easily check here that these three do in fact add up to the total. In this case, it's a series circuit, so I know that the resistances should add up to this, but we kind of use that to find this in the first place. But I can also check my power. I know that the power dissipated by R1 plus R2 plus R3 should give us the total power dissipated, and again, you can check, and you should be able to see fairly easily that it does indeed check out here. So this table is a nice way to consolidate everything. It allows you to figure out what you know, what you don't know, and what you need to find in order to figure out what it is you want to know. For example, if I were particularly interested in finding this, well, I started with my total EMF and my individual resistors. And so if I want to know the voltage across R2, it means I'm going to have to find the current through I2 first. To find the current through I2, I need, in this case, to find the total current. And to find the total current, it means I need to find the equivalent resistance of my circuit. Once I have the equivalent resistance, I can find the current. And once I have the current, I know what this current is. And now I can use V equals IR to find the answer here. And I don't have to worry about anything else if that's all I was looking for. I don't need to worry about this or this or this or this or any of the powers if all I wanted was this. So this chart is just a really, really handy way of keeping track of all the information you have. And it not only keeps track of the information, but it helps you figure out what to do next. I like this method so much that I started to use it. It helps me avoid making silly mistakes. So even if you feel very confident, like, oh, I can just use the loop rule, it's the same thing every time, and I can make that work. You can, there's nothing wrong with it. However, I strongly recommend for every single one of you without exception, using this kind of system. It really helps you consolidate all the information you have. It helps you avoid making stupid mistakes. It helps you avoid doing extra work when you really didn't need to. Again, I do this now. I didn't used to. I learned this when I was looking for ways to teach this topic, but now I make VIR charts because it helps me. Now let's see how all this plays out when talking about parallel circuits. First, I want to take a couple minutes and I want to go through the derivation of the equivalent resistance of parallel resistors. Hopefully, many of you have already figured this out based off of the previous lab activity or based off of the notes that I shared with you. If you are totally comfortable with it, feel free to skip ahead. The first thing to note is because the battery and the two resistors are connected in parallel with each other, the voltage across each of them is going to be the same. And again, this is because as long as we treat the wires as having zero resistance, there's no change in potential from the top of any of these elements. So the top, they're all at the same value of potential. And at the bottom, they also have to all have the same value of potential. And so the difference across them has to be the same. Next, we can make use of Ohm's law to rewrite V1 and V2 in terms of their currents. Note that their currents are not equal to each other because the current through the battery is split between the branch 1 and branch 2. But that gives us the relationship that the total current through the circuit is equal to the sum of I1 and I2. If you look down at the equivalent circuit at the bottom, though, we see that the current, the total current through the battery, can also be written as the EMF of the battery divided by the equivalent resistance of R1 and R2. Since the equivalent resistance is what I'm looking for, I'm going to rearrange the equation to isolate R12, and then we can plug in the values that we got found from up here, and we can simplify. If I had even more resistors hooked up in parallel, for example, if I added a third branch up here, the same exact process would hold. I1 times R3 would still be equal to the EMF. The total current through the circuit would now be split three ways. There would be a plus I3, and I would end up with another term in the bottom. And so the equivalent resistance for resistors in parallel can be expressed as 1 over the sum of the reciprocals of all of their resistances, or we often write it as the reciprocal of the equivalent resistance is equal to the sum of the reciprocals. Note that if there are only two resistors in parallel, this expression actually simplifies nicely. You can write it as the product of the two divided by the sum of the two. There is no corresponding simplification for three or more. You can take this and you can simplify it, I guess you could call it that, but you end up with a big ugly mess. There are multiple terms, and it's not worth doing. But if you have two, it is convenient to know that this is one way of calculating the equivalent resistance. Again, only for two resistors. Now let's go back and let's analyze the circuit using a VIRP chart. Let's start once again by inputting the things that we know, which again, like last time, are the voltage of the battery and the resistances. In order to keep going, I need to have at least two of the three columns filled in any particular row. One thing I could do is I could fill in the equivalent resistance down right here, but in this case, the easier thing to do is to make use of the fact that these resistors are in parallel with each other. Because they're in parallel with each other and with the battery, I know that the voltages across the resistors R1 and R2 must be equal to the voltage across the battery. That allows me to easily figure out the current. In each one, it's the voltage divided by the resistance. And because the total current is equal to the sum of I1 and I2, we can write this as E times 1 over R1 plus 1 over R2. I ran out of room. And we can confirm that this is, in fact, equal to E over the equivalent resistance, where again we can calculate the equivalent resistance as 1 over R1 plus 1 over R2. Calculating the power dissipated by each resistor is pretty straightforward. We didn't even need to find the current. In this case, using V squared over R is the simplest because we know R and finding V was really easy. And so the power is equal to the voltage of the battery squared divided by R1, the voltage of the battery squared divided by R2. And the total, we can calculate one of two ways. We can either add up power 1 and power 2 to find the total, or we can use the voltage of the battery squared divided by the equivalent resistance, and in either case we get the same result, which is simply this. At this point we can also confirm that the currents I1 and I2 do in fact add up to the total current. We could also confirm that the total current satisfies Ohm's law with the total voltage of the battery and the equivalent resistance of the circuit. With series circuits, I was the same for everything, and V added up. With parallel circuits, V is the same for everything, and the currents add up together. And in all cases, the sum of the individual powers need to be equal to the total power, regardless of whether you calculate the total power using the equivalent properties of the circuit or by adding up each of the individual pieces. Parallel circuits have interesting properties. There are normally a lot of really good demonstrations that I would do for this unit. Unfortunately, I can't do them. But you'll note that R1 and R2 draw an amount of current independent of each other. The current through R1 is simply the voltage of the battery divided by R1, as if R1 were the only thing connected to the battery. If I had drawn the circuit without R2, R1 would draw the same current. Adding R2 draws extra current from the battery, but it gets split between R1 and R2 so that they get the current that they demand individually. This makes parallel circuits really useful. In fact, parallel circuits are probably more common than series circuits. Consider your home. When you turn on a light, do all the other lights in your home dim? I hope not. They probably you have 2 lights on, 3 lights on, 4 lights on, 1 light on. No matter how many lights you have on, they all have a fixed brightness. That's because they're all connected in parallel. That way, when you turn on a light in one room, it doesn't dim the lights in another room. Can you imagine living with other people like that? Or consider a television, right? A television doesn't work unless it's drawing a certain amount of current. And if someone else starts microwaving, if they were connected in series, nothing would work. The microwave wouldn't work, the television wouldn't work. They would both be competing and ultimately not getting the amount of current they need. So in a household circuit or in a building circuit, it's actually uncommon to ever find anything connected in series. In a particular device, you would have maybe resistors in series, or maybe again in like a toaster oven, you might have some elements in series with each other. But generally speaking, they will be connected in parallel so that they each operate independently of each other. Each of them has a resistance designed to draw a certain amount of current through it. Again, if I disconnected R2, the current through R1 would remain the same, and so the power through R1 would remain the same. And as a result, the brightness, if this were a light bulb, its brightness would be unaffected by the presence of R2 or not. If I added a third bulb, the brightness of R1 and R2 would be unaffected by the third bulb, and so on. If, however, we look back at our series circuit, the current through R1 depends on R2, right? It depends, and on R3 in this case. It depends on the equivalent resistance of the whole circuit. The power through each one depends on the resistance of the whole circuit. And so by adding or removing resistors in series, you dramatically affect the properties or the behaviors of each of those resistors. If I add more resistance to the circuit, I'm going to increase the overall resistance, which will decrease the overall current. And since we can express power as I times V, the voltage of the battery is remaining the same. If I increase the resistance, the power will go down because I will go down. On the other hand, if I wanted to talk about the power of just R1, if I increase the resistance of the circuit by adding another resistor, for example, the total current goes down again. If the total current through R1 goes down, then the voltage across R1 goes down. And since power is equal to V squared over R, V goes down, power goes down because R is the same. Or, since the current through R1 goes down, and P is I squared R, once again, R is constant, I goes down, power goes down. So we can analyze how the power dissipated by individual bulbs or resistors is affected by adding or removing other resistors from the circuit. And again, the behavior is very different with resistors in series compared to when we have resistors in parallel. This gets me to power of a light bulb. So what determines the brightness of a light bulb is the rate at which it uses energy, right? Put in more energy, I get a brighter bulb. If any of you have ever gone shopping for a light bulb, or maybe you've replaced light bulbs in your home, you'll notice that they're rated according to something called wattage. A 60 watt bulb or a 120 watt bulb are very common. 40 watt bulbs are a little bit dimmer. These are ratings of how much power those light bulbs use. A 40 watt bulb dissipates 40 watts of electrical energy in the form of light and heat, whereas a 120 watt bulb dissipates 3 times that, and so it tends to be about 3 times brighter. But light bulbs are essentially just resistors. Sure, their resistance might change a little bit with temperature, but that doesn't really matter. If a light bulb is a resistor, then it obeys Ohm's law. At any given moment, at whatever value its current resistance is, V is equal to IR. And that means the power used by the light bulb is equal to I times V, which is equal to I squared R, which is equal to V squared over R. But again, the light bulb is essentially a resistor. It has an effective resistance that's determined by the properties of the light bulb. But if R is determined by the properties of the light bulb, then how can I make a 60 watt bulb? If I have a 60 watt bulb, but the power depends on V and R is determined. And it's not like the light bulb is generating its own voltage, it's being given a voltage by some external source. So what does this all mean? Well, what happens is that a light bulb, a 60 watt light bulb, is not really a 60 watt light bulb. It is a light bulb that will draw 60 watts of power if connected to a 120 volt source. So a 60 watt light bulb will only draw or use 60 watts of power if it's connected to a 120 volt source. That allows us to calculate the resistance of this bulb, and we get that the resistance under these circumstances are 240 ohms. So a 60 watt light bulb is really a 240 ohm light bulb. This seems totally arbitrary and somewhat crazy, right? Why would we do that? Well, there are 2 reasons. Where does the 120 volt come from? Well, 120 volts is the standard voltage supplied by the U.S. electrical grid. So in the United States of America, the wall outlets that you use are rated to provide 120 volts of voltage. Other countries don't use 120 volts. A lot of Europe, for example, uses 220 volts. There are some countries that use 100 volts. And so a 60 watt light bulb in the United States is not a 60 watt light bulb in one of these other places. Because if I put 60 watts over here, or rather, if I put 240 ohms over here and 220 volts up top, I get a different power output. A 240 ohm light bulb in a country that uses a higher standard voltage will actually be brighter in that country than it would in the United States. Or if I hook up a 240 ohm light bulb to a 60 volt power supply, it will be dimmer than I expect it to be. So why do we rate light bulbs according to their power output if their power output depends on what we connect them to? The reason why we do that is marketing. Because a higher resistance bulb has a lower power output, right? P is equal to voltage squared over R. Voltage is fixed by your power supply, and so power is inversely proportional to R. And so if you market bulbs according to their resistances, oh, this bulb is, more resistant than that one. It has a bigger number. It must be brighter. I guess people found that it was confusing, and so light bulb companies marketed their bulbs according to their power instead of according to their resistances, for better or for worse. All right, hopefully you learned some new things, and hopefully some other things have been clarified by this video. We will continue to apply a lot of these principles in subsequent lessons. We've got a few more things to cover, but at this point we have the foundations of the topic of circuits pretty much under control. Till next time.